Section 13.8 is on extrema of functions of two variables. So we're thinking about, well, like you just had for homework, z equals f of x, y. So yeah, I guess we're not very interested in the example on the board here. Well, maybe we are. But I'll show you pictures that we are more interested in. And on the group work that I passed out last time that we started, and I think we're going to work more on it today, we talked about critical points. And we mentioned that, hey, these critical points, the same stuff you did in Calc 1, you're going to do in Calc 3. And that's kind of what I want to show you today. But I want to show you how, because there's a couple of differences when you have extra variables involved that you didn't have to worry about. Here's a nice picture from the book, so I thought I want to show you this. Here's my surface. Z is a function of x and y, right? Z tells me how high I am at any particular input. And so you can have a maximum and you can have a minimum, right? Now this is what's called a closed bounded region R. Okay? Let me use those words carefully. A region, that's just an area. That's not a big deal. When I say bounded, do you guys understand what I mean? It doesn't go to infinity, right? Like back in the day, when you guys did y equals 1 over x and you graphed it in Calc 1, and you had this little graph like that, one of my favorite things to do is to have people, well, let's do 1 over x squared so it actually works. I like people integrating from 0 to 1, 1 over x squared dx. And when they do that, what are they doing? Well, they're finding the area under, I guess this was Calc 2 when you did this, under the curve, but that is not a bounded region, because that region goes infinitely high, right? And yet, we learned that that is a finite integral, so that was kind of cool. So one of these works and one of these doesn't. I'm blanking right now. I guess this one's infinite, the one I drew, and this one's finite, right? Okay. Well, we want a bounded region. And when I say closed, it's funny, I feel like I'm just doing a lot of math vocabulary, but that's okay. That's why I did linear all day today, too. Closed, well, it means the same thing that it did. In Calc 1, you had a closed interval, and you had an open interval. Do you remember this notation? Like the difference between 3, 5 and 3, 5. What the difference is 3 less than, I'm sorry, this one is 3 is less than x less than 5. And this one is 3 less than or equal to x less than or equal to 5, right? That's the difference between closed and open. And the picture was, well, here we color in the endpoints, and here we use open circles, right? You guys remember those pictures from Calc 1? Same deal here. If I have a closed region, that means I'm including the boundary. Too bad I can't draw it. But I'm including those points right on the boundary. Right. Yes. Not that I necessarily want to call them critical points, but I think what you're saying is, hey, where does the minimum occur? And you might remember that, well, we would look for critical points, but we also used to test these endpoints, because maybe the smallest value is at one of the endpoints. Well, the same thing happens here. Maybe the minimum value is at one of the, quote, endpoints. Now, what's an endpoint, though? How many endpoints are there? Are there infinitely many? Yeah, maybe. Or maybe I'm in better shape. Maybe there's only 4 in this picture. In other words, maybe I know that the vertices are the important deal, and And I'll tell you this, in another class I teach here called finite math, when we do what's called linear programming, which is the first step at optimization, the vertices end up being the important points. But you're right, there's infinitely many points on the boundary of this region, and so we'll have to see what happens. Okay? All right. Hey, that's what I just said. So I talked about closed. Oh, the extreme value theorem. I think you probably saw that in Calc 1, but I really doubt you remember it. Deals with a region in the plane that is both closed and bounded. So now I explained those things. And I guess I explained bounded. So that's good. I feel like I did my job. All right. Here it is. Right out of the section 8 of the book. Theorem 1315. Let f be a continuous function. Yeah, we always need continuous if we're going to do calculus, right? Of x and y defined on a closed, bounded region. Okay? So we said that we need closed and bounded. Then, there is at least one point in R at which f takes on a minimum value, and there is at least one point in R at which f takes on a maximum value. Okay? That's kind of neat. If you have an unbounded region, that doesn't have to happen anymore. Okay? I mean, think of that elliptic cone example that Garrick asked about before class. I guess it was a circular cone. But because it's positive, because the square root's, right, there's a positive sign in front, this is a circular cone, and we're starting at the origin, right? So if I just take some square or some closed bounded region, and I say, okay, guys, where's the minimum in that region and where's the maximum in that region? This theorem tells me they exist. I can talk about the minimum value in that region, which I guess if it includes 0 would be 0. And I could talk about the maximum value in this region, which basically, I guess, because of the symmetry, would be at whichever corner is farthest from the origin. So I think that that output would be the maximum value. Right? You guys with me on that? You're talking about the mean value theorem, or the? That's what that was the mean value theorem. Yeah. And then there's something called the intermediate value theorem. So this is why they're very confusing. Yeah. But that's the mean value theorem. Well, let's pause and look. So we found out it was Rolle's theorem that we were talking about. All right. Let's move on. Definition of relative extrema. Don't write this down. It's in your book. I think you know it anyways. They tell me, hey, f has a relative minimum if... Now, I almost didn't include this, but I did put it on the PowerPoint because I want to bring up an important point. When we talk about relative minimum or relative maximum, we're talking about an open disk or an open region of some kind, not a closed region anymore. Okay? That means don't include the boundary. Right? So let's show you the picture. Where's it at? Here. Nice picture. Don't ask me what equation that is. I don't know, but you can get that from Maple or something like that. Z equals, who knows. But I think, if I'm understanding the picture right around here, you guys see this black dot? Right around there, I have what I would call a relative, maximum. Right? Everybody seems to be nodding their head and just fine with that, right? We understand that. It's not the absolute maximum. The absolute maximum, or the global maximum, if you want, is right there on the z-axis. But that's a relative maximum. Why is it a relative maximum? because there exists an open disk so that if I look at all the outputs for that open disk, this is the biggest of them. Yeah. So we are, in this section, imagining that z is a function of x and y. You're right. You could say x is a function of z and y sometimes, and maybe that helps. But for this section, we're not doing it. Because we could always take your function and just tip it. I don't have to worry about it. Okay. Moving on. Critical point. I gave you this, right? This is from the book. I just decided to give you that in the group work. So what's a critical point? One of the following is true. Either both partials equal 0, or one of the partials doesn't exist. Those are all critical points. Those are points to check if you want to get a maximum or a minimum in a sense. Okay, this is the slide that I included because I wanted to show you what we're skipping. Okay. Let me move this picture out of the way for a second. Get my arrow back. Okay. Not working at all. Yeah, I don't want to do that. Guess I have to. Okay. What I wanted to say was this. There's a symbol we haven't seen yet, okay? So don't worry about him yet, but you notice what it is. We take the partial derivative, the x partial derivative, and we take the y partial derivative, right? And if both of those are 0, then it says every directional derivative must be 0. Now, what the heck does that mean? Well, you notice they drew the surface. And then at the maximum point there, they drew a tangent plane. Now, yeah, let me have my pen back. The partial derivatives, remember, are tangent lines. This, right here, when you're treating y as a constant, that tangent line is the x partial derivative, right? Whereas this tangent line, you get its slope from fy, right? So you have the partial derivative giving you the slope of this line, the partial derivative giving you the slope of that line. It turns out that you can kind of then take linear combinations of these. You can take sums of these, or maybe more of the x than the y, and you get other vectors in the tangent plane. Okay, so this is what we've skipped. Yeah, at any particular point, we know we can compute an x partial and a y partial, right? Well, these define a plane. Okay? And so we're going to be talking about that plane eventually, that tangent plane. Well, remember that in Calc 1, we had functions like y is the absolute value of x, which might be the, might be analogous to a cone. And remember that right here, the function was not differentiable, right? So we may have places where we can't do exactly what we want to do calculus-wise for various reasons. Okay? So things like that will happen. Okay, moving on, because I don't really want to do too much on what we are skipping. It appears that such a point, what kind of a point? A critical point, is likely location of a relative extremum, and this is confirmed by theorem 1316. If f has a relative extremum at a point on an open region, then x naught, y naught is a critical point. So if it's a closed region, you have to test the boundary points. But if it's an open region, we know what's going to happen at a critical point. Understand the difference? And that was true in Calc 1 also. Okay. The second partials test. Don't write this down. Please. Matter of fact, I left a blank slide because I'm going to show you what to write down. Okay. But, back to here. This is in the book. What's the deal? Second derivative, right? What do we do with second derivative in Calc 1? Find concavity. And if the curve is concave up at a critical point, what does that tell you? You have a minimum. And if the curve is concave down at the critical point, you have a maximum. What else could happen? Yeah, if the second derivative is 0, you don't know, do you? Yeah, you don't know. It could be a point of inflection, although actually you have to check the third derivative before you know that. But, yeah, the you don't know squat, I guess, is one way of saying it. Yeah, we're not sure. We're not sure. Okay. So we're going to have a test like that. Some books call that the second derivative test. We're going to have a test like that using the second partials. Now, how many partial derivatives are there when you start taking second derivatives? Yeah, we have fxx, fxy, fyx, and fyy. And did you guys do this a lot on the homework or not? Or a little bit? All right, we're going to do more today then. We really have to do something. Okay. So here's what it says. Good for you. Do you know what mod means now? What does it mean? Elaine called because she was worried, yeah, but she didn't want to do every problem, so. That was nice. So mod 8 means, yeah, so if you did problem 15 first, was that what you did first? Or did you do 7? Then the next one you do would be 15. Yeah, cuts down the amount of work you have to do, and you get a nice smattering of problems this way. And plus you had a day off. What are you going to do? You know, President's Day. Good day to do calculus. Okay, so let's see. Suppose that these partials equal 0. Okay, we're at a critical point. Then you can test for a relative extreme, and it says consider the quantity blah blah. I said don't write that down. Okay, let's do this instead. Let's do it here. Instead, let's consider the matrix. No, the quantity is fine. But it's the determinant of this matrix. F, X, X. Let's see, row X. So F, X, Y, F, Y, X, and F, Y, Y. Let's consider that. And what I mean is all these functions evaluated at A, comma, B. Okay? Now, if I have that, then these conclusions work. So by D here, all I have to do is do the determinant. Now, when I say determinant, you guys know what I mean, right? I do fxx times fyy minus fyx times fxy. Okay? Yeah, why do they have that? When? I mean, that's a good question. Are fxy and fyx equal? Did anyone notice that at all in the homework? When did it happen? Problem 63 it happened, right? Zxy and zyx were the same. Did it ever happen again? There was another one where it happened? All right, well, here, let's do a little more work and we'll see. Remember this problem? Remember this little thing I was giving you guys last class? I brought it back. My 3 nice examples I had pictures of. Z equals x squared plus y squared. Z equals 1 minus x squared minus y squared. So these were paraboloids. And z equals y squared minus x squared. That was that. What was that? That hyperbolic. It was an example of a saddle point. Okay. So all 3 of these functions have exactly one critical point at 0, 0. So what I want to do is I want to test what kind of critical point we have. Okay? So what do? I'm going to need some functions. So I need zxx, and that equals 2. And I need zxy, and that equals, well, what this means is take the 2x, take the derivative with respect to y. And of course, that means we're treating x as a constant, so yes, it's 0. And zyx is and zyy is 2. Okay. Could you guys take a minute and do the partial derivatives for each of those? All right. So what do we get? Let's see. Negative 2, 0, 0, and negative 2 for the 4 quantities. And here, you got negative 2, 0, 0, and 2 for the 4 quantities, right? Okay. So it doesn't usually work this way. Usually when you take partial derivatives, you don't get numbers. What do you get? Functions, right? You get some function. This is the simplest example I could come up with. And so the functions are all constants. It's kind of like in Calc 1 when you decide you're going to do y equals x squared. Why? Because you want to demonstrate what a minimum is. So then you do y prime is what? 2x. And then you take the second derivative and you get what? 2. So it's concave up everywhere. That's why the parabola looks like it does. Does that make sense? Okay, so I'm doing the same kind of example here. And so now what I'm going to do is I'm going to compute D. And so D is, well, the determinant of, in this example, you don't have functions, you just have actual numbers. Usually, what you would do is you would put down, you have these functions, and then you have to insert an x and a y. Now, which x and y would we be using? If we were going to evaluate these functions at an x and a y, well, you want to go at the critical point. Does that make sense? What's that? Yeah. No, you want to do critical points even if you're just talking about a relative. Yeah, for an open, you want critical points. If it's closed, you also test the endpoints. That's the difference. Okay. What's this determinant? 4. Now the determinant 4 is greater than 0. So that tells you you either have a max or a min. All right, so let me go back and write some of this down. If D is greater than 0, we have either a max or a min. If D is less than 0, well, one way to say it is that you have a saddle point. I'm going to say this, to be a little more precise. There exists, let me say this, for any open disk containing the critical point, there exist points x, y, they call it x1, y1, and so if I have I guess I need to name the critical point. Shoot. Critical point x naught, y naught, we'll call it. There exist points x1, y1, and x2, y2 such that f of x1, y1 is less than f of x2, y2. No, I'm sorry, f of x naught, y naught is less than f of x2, y2. What am I getting at here? You have your critical point, x naught, y naught, okay? You have, for any size disk you want around it, you could find something that has a lower output and something that has a higher output. Now, in the case of a saddle point, that's actually what happens. Show you the picture again. Okay, here they are. Didn't show. How come? I think I know why. Shoot. Here we are. Right? There's the critical point, 0, 0. If you take any size disk around that critical point, some of the outputs are higher in the disk, and some of the outputs are lower for inputs in that disk. The reason I don't want to call it a saddle point is that it doesn't always look like a saddle. You might have one little stripe where things are lower and everything else is higher, or vice versa. Okay? But this is your classic example. They call this a saddle point. Questions on that? Okay. Back to this. Do that. Oh, let's finish our... oh, that's if D is less than 0. What if D equals 0? No conclusion. So then we can't tell if we have a max or a min. At least not from this test. All right, so back to our little examples. Notice if you do the determinant for the second one, you also get 4, right? So again, there's either a max or a min. And for the last one, That's where you get -4. Yeah, this is where we have the saddle point. That's actually the picture I showed you. So I guess the question that remains is, well, how do you figure out if you have a max or a min? Well, you could tell from, see, here's the thing. When I say that D is 4, it's kind of like, okay, I'm either concave up everywhere or concave down everywhere in every direction. And so what I do then is I look at one of the partial derivatives. So here, since zxx is greater than 0, okay, we have a minimum. And that should make sense to you, because remember that the second derivative being greater than 0 makes me think concave up, right? When I say zxx greater than 0, see, all I've been doing, if I do zxx, I only did calculus 1 on the function. And so I was staying in a certain plane. And so if I look at the picture again, let's show you that picture again, please. Oh, I lost it. Uh-oh. Yeah, if I just stayed in a certain plane, I would get a parabola. And so that's what zxx is telling me. And so if you have D is positive at the critical point, then you could just check out one of the derivatives, one of the second derivatives. Same thing with this one. Here, since that's negative, concave down, I have a maximum. So these are the kind of things you look for. Okay? Questions on that? All right. I guess we're at break. When you come back from break, so back in algebra class you called these word problems. Now we call them applications. Okay. So let's see. How about I get a pen out? So I think I want to do problem 9 from your book. And there's a reason. It's because there's a history. So when I used to teach over at Case, and I guess I was there for 5 years, I taught a number of different calculus courses, but this was one of the topics I got to teach quite often, was how you can find extrema for functions of more than one variable. And Case did this with their applied calculus classes as well as their standard calculus classes, as well as their honors calculus classes. I mean, everything we taught there, this was a standard topic, is, hey guys, functions don't always have one input. They have more than one input. Let's learn how to do calculus with them. Okay? And here was a prime example. And I used to use this problem. I don't remember where I got it, but I know I verified this on the internet, which if you just read problem 9, you wouldn't know this. Problem 9 says maximum volume, the sum of the length and the girth. What's the girth? Yeah, kind of a package carried by a delivery service cannot exceed 108 inches. Now, what I almost did was what I used to do with the Case class, and that is we would go to the internet, which we could do in the classroom back then. Isn't that cool? So we could go to the internet, and we could go to the U.S. Postal Service website, and they would have their rates for various size and shape packages. And the standard rate, so you don't have to pay extra, what it said was, hey, length plus girth is less than or equal to 108 inches. So this came right from the U.S. Postal Service. And then I got to Lakeland. And my first year, they let me teach Calc 3. And I was like, wow, there's my example problem, problem 9. So I can't remember if I assigned it or not. I don't know. But I decided this year I want to use it again as my example problem. Okay? So that's why I picked it. Now, yeah, question? Well, okay, so when we say this, we're saying, first of all, we have a rectangular package. Perimeter of a cross-section, yeah. So let's look at it. I mean, the girth is the size belt you would need to carry it. How about that, right? So if I have a rectangular box, well, let's see. Something like that. Here is my length, L, right? And then, I guess the girth is the size belt I would need to put it around that way, right? So, okay, if we're using X's and Y's, yeah, or maybe W's and H's for width and height, the girth, I guess, is 2W plus 2H. Right? Is that okay? All right. And I want the sum. So my function I'm dealing with, f of LWH, is L plus 2W plus 2H. Okay?
So if you felt like you could send like a 104-inch long box, it's like 1 by 1 inch.
That's right. That's right. So you could send one of Matt's pulls for the pull vault, maybe. Although it's probably pretty short, 104 inches. Well, anyways. Yes, that's the idea. You're not charged extra. Okay, so, and actually, Jay, you did exactly what I used to do.
It's just a weird, like, someone wouldn't send it.
I know, but we used to do the same thing in the case. Every year someone would ask, well, wait a minute. If I make the length equal to 0, look how big a flat square I can send, right? You know, it's kind of fun. All right. What? How big a piece of paper can you send? Okay, an envelope. I guess I shouldn't say equals F. I should say L plus 2W plus 2H equals 108. Right? Why? Well, because what I'm trying to do, it tells me in problem 9, I'm trying to maximize the volume. How much stuff can I send in this package? So let's maximize the volume. And this is an example of what's called optimization. Maximizing or minimizing. Optimization is a huge field. You can major in optimization. You can get your master's in it. Probably your doctorate. Okay? At Weatherhead, actually, my wife's degree was operations research, but half of what she did was this. Okay. So, yeah, so I like to advertise that, hey, this is an important field when we do this. Okay, so we're optimizing. So how do we maximize the volume? Well, we need to write a function for volume, and of course volume, well, I guess volume equals length times width times height. Right? Of course, now volume is a function of 3 variables, so I'm kind of beyond what I'm supposed to do in this chapter. Although you can do everything the same, just that your matrix of second partial derivatives is 3 by 3, and it all works. Okay, but that's not what we're going to do. They tell me something here, right? Well, I think what you're going to do is kind of use this relationship here and turn it into a function of 2 variables, right? Because what can I solve for very easily? L. And so where it used to say L, we can now write that we have a function of just W and H. You guys see that? So what am I going to put for L? Well, I'll put 108 minus 2W minus 2H. And then I have W and H here. Okay. So V of W and H is 108 WH minus 2W squared H minus 2WH squared. Okay, what's the next step if I'm trying to maximize the volume? Let's take partial derivatives. So I guess I have dV dW. Let's write it this way. Oh, sure, that's a good idea. Let's simplify V. So V is just 2 times 54WH minus W squared H minus WH squared. I like that idea, Linda. So now what I'll do is I'll call it VW. That's the partial with respect, and that's going to be a function of W and H. So it's going to be 2 times 54H minus 2WH minus H squared. Right? And similarly, VH of WH is 2 times 54W minus 2W minus 2WH. W squared, yep. Thank you. W squared. Okay, so now we have the partials. And what's next? Why did we find the partial derivatives? We want to find a critical point, right? So we find where they both equal 0. Oh, both have to equal 0. Well, good thing, because I have a system of equations here. How many variables are there? 2, and there are 2 equations. So I might be able to find some solutions. And there's some quadratics there, so you might be able to find multiple solutions. It's kind of interesting. Yeah, you set them equal to 0 and solve, just like you did in Calc 1. The other thing you look for is where these things are undefined, but that's not going to happen. Okay, so my system of equations, if I take a look at the first one, I can write H times, let's see, 54 minus 2W minus H equals 0. Similarly, I get W times 54 minus W minus 2H equals 0. Right? Now, it's interesting. One solution you're going to get is by letting the height be 0, or by letting the width be 0, which means you're going to let the volume end up being 0. That's your minimum. You can make the volume as small as you want. Okay. So the more interesting solution is this. From the first equation, 2W plus H is 54, and we also need W plus 2H is 54. Okay? And this could be solved very easily. When it's all said and done, let's see if I can do that quickly in my head. I basically have 3 of the same thing. I think I get 27 for W. No, that's not right. 18, 36, 50. I think I get W equals 18, H equals 18 after a little bit of work. And then I come back up here, 36 and 36 is 72, which which would mean that WL is, so then go back up here. 108 minus 72 is 36, so I get L is 36. No, we don't know it's a maximum. How do we figure out if we have a maximum or a minimum? So we'd have to take the second derivative, right? Of course, if you notice, when you take the second derivative, all right, if I take, for example, VWH, I get negative 2W. And that's going to be the same as VHW. Okay? And I can also do VWW. Oh, no, I screwed up. 54 minus 2W minus 2H. That's what that is. And this one is, that's my negative 2H. And V of HH is negative 2W. Yeah. So what you do now is you put your 18s in here, and when you work it all out, you'll see, oh yeah, it's greater than 0. And then you'll check this thing is negative. And so that means it's concave down. And I realize that was a lot very fast, but we're kind of out of time. Either one works, yeah. Either one works. Once you know that your D is bigger than 0, look at either of those, WW or HH. You have to plug in, yeah. And yes, then, or go ahead and do the determinant on these algebra equations. But it's more work. Although you will learn things by doing it if you actually do the algebra, because then you could figure out what makes it positive and what makes it negative. But no, it's easier to put the numbers in and then take the derivative. Take the determinant. All right, guys, we will do more from this section some other time. We did this section a while ago. Actually, we hit it very early, remember? I think we covered partial derivatives, and then I jumped right to section 8 and said, what do we use partial derivatives for? To find maxes and mins of functions of 2 or more variables, right? And then we actually did some applications. And then we kind of put them away for a while, and then on homework for today, you guys tried them again. How did they go? The homework for today. 13.7, the gradient, yeah. This 13.9, yeah, okay. And I guess, I'm kind of trying to demonstrate that look, these are not easy. We're going to give you a big tool today to handling optimization problems called Lagrange multipliers. It's the last section of the book, or of the chapter, I should say. And we'll be able to, actually for homework, you're going to revisit some of those tougher problems again and try them in using this other technique. And then you can compare and see which method you like better for these problems. So let's see. I remember doing this problem with you guys, right? You guys did one like this for homework? I think you did problem. Did I assign problem 9? Okay. So maybe this was it. And then problem 10 was similar, except that, yeah, you're minimizing cost or something like that. And if you want to minimize cost, actually that could be kind of like this pop quiz I gave where you want to minimize surface area because it costs money, for the various building materials. But if I remember right, number 10, didn't it have, you paid different amounts for the different pieces? And that makes it a little more challenging, a little more fun in a way. All right. You're going to go back to that problem again for Thursday. Okay, and we'll try it with these Lagrange multipliers. Now let's see. When I did this section with you guys, did I talk about this example? Finding the maximum volume of a box where Did I do this one with you guys or no? Oh, okay. Well, then this is worth showing. This is the example one right from your book, okay? But I'll just talk it out a little bit. This, you have a plane drawn, right? And a plane has an equation, ax plus by plus cz equals d, let's say, okay? And you're allowed to pick any point in the first octant, if you want, on that plane. And when you do, you automatically get a rectangular box, right? So they picked one right here. So I guess the question here is, where should I pick my point to get the maximum volume of such a box? You know, maybe I should pick it up here, because then I'll get a taller box. But I guess the downside is, well, it won't be as fat as that blue one, right? So which would have greater volume? Or would they all have the same volume? Well, you can convince yourself pretty quickly that's not true, right? Because you could pick one up here, which is going to have, well, you can make the volume as small as you want, right? By getting closer and closer to that point, which is the vertex. So yeah, where should it be? And this is a good question. Right? What do you mean the middle?
Like, you know, that the longest sides.
Okay. Well, to make the z the longest, of course, I go up here.
You want all sides to be.
Yeah, but I can't have that, right? Because as soon as I start making x and y bigger, I come down. But you're right. I agree with what Jay said, that the answer is going to be in the middle somewhere. But where? You know? And so they work it out for you in the book. Let me kind of just zip you through it. So they say let x, y, z represent length, width, and height, which is what you guys just did. Because one vertex of the box lies in the plane, you know that what? Well, that z is this. So they took the equation of the plane and they solved for z, right? So what do you think they're going to do next? What are we trying to maximize? Yeah, so my volume is v equals x, y, z. So what are we going to do? We're going to take this mess and put it in for z. So now we'll have volume just as a function of x and y. Why? Because we are constrained. We have to have a point in the plane. So the z must be equal to 1/3 24 minus 6x minus 4y. Right? So now you can make it a problem where you have a function of two variables, and they throw it in there right where I wrote. Okay. So now, what's that say? Well-placed little box there. Okay, here we go. Yeah, so they simplify, right? Instead of z, you get this, and then they distribute the x and y. And let's see what happens. Set the partial derivatives equal to 0. You guys are good at that. Okay. How do they get this? Yeah, I mean, this is something that you could give an algebra student, right? This mess right here. There's two equations. Of course, there's one thing rather annoying. Your algebra student wouldn't be very happy. What kind of equations are they? They are called nonlinear, right? I mean, if you distribute that y, well, I understand we're going to get 0, 0. I can see that, right? I guess what happens is I get, say from the bottom equation, I get x over 3 equals 0, or, and then this equation gives me 24 minus 6x minus 8y equals 0. So going with this guy, I get 6x plus 8y is 24. Okay? And then going with this guy, I get 12x plus 4y equals 24. And then maybe you could solve and come up with that answer. Right? That's kind of the idea. You guys follow that? Okay. So moving on. At 0, 0, the volume is 0. Yeah, no kidding, that's not a maximum. Okay. at 4/3, comma 2, and this is what some of you guys were asking me about the day that we did the mailing problem. You said, well, wait a minute, how do you know if it's a maximum or a minimum? Well, they're going to go the distance here, and they're going to do that test with the second partials. So they do all 4 of these things, put them in a matrix, take the determinant, and they get 64/3, which is positive. What's that mean when you get something positive? Well, it means it's a max or a min, as opposed to what? Like not a saddle point, right? Remember, if it was negative, you have, in any neighborhood you draw around the point, you have things that are above and things that are below. That was the idea. But here, no, I'm either at the top or I'm at the bottom of my neighborhood. And so what I do is I look at just, VXX, because then I'm just doing Calc 1 in a sense. I just took the second derivative in the Calc 1 world. And since it's negative, that means concave down. And concave down tells me what kind of point did I just find? Maximum. Okay, so these are all things that we covered. And so we conclude that the maximum volume happens at that critical point. So now they work out what it is. And they get that the maximum volume is 64/9. Now, I guess let's go back to what Jay was saying. He said, well, the answer is going to be in the middle. I mean, is it? 4/3, comma 2. On that, if you look in that picture, is that about where you'd pick it? I don't know. These are good questions. And then I guess what I'd be interested in is this. What's the relationship between these x and y coordinates and the original equation? And maybe there's some snazzy relationship. I don't know. But we could do that another time. Note that the volume is 0 at the boundary points. Yeah, we said that. Okay. So yeah, I want to do a problem with you. But I want to, I'm going to skip, should I do the least square stuff first? Yeah, let's do it. It's all here. There's another major topic in this section that I skipped. This is section 9 still, 13.9. When I say major topic, it's not a major calculus topic. Matter of fact, a lot of calculus courses don't even cover it. But it is a major topic in mathematics. And I just feel like I wouldn't be doing my job if I didn't at least mention it. So how many have heard before of the method of least squares? Then I'm really glad I'm mentioning it. Okay. So this is something that you would learn, for instance, in a statistics course. Something that a lot of students will see in high school in a science class. It's the way that you take data and write a mathematical model that almost goes through the data in a sense. It's regression, yes. It's also called linear or, well, other words too. A lot of times we do linear, but it's regression. So you have seen, so Clayton has seen regression. How many have seen regression before? Okay, so it's just terminology. But half of us haven't. All right, so let's see. What's going on here? Well, like I said, examples involve mathematical models, right? How do you come up with the model? This is what everyone's asking me in the applied calculus class. Who came up with this model for profit? And how'd they do it? And I always tell them, well, that's who's getting the big money, isn't it? Right? I mean, they're the ones that came up with the thing that you're taking the derivative of, right? How do they do it? Well, again, there's more than one way, but one of the most important ways is what's called the method of least squares, also called regression. Okay? And here's the idea. Suppose you have some data points. So here are, let's see, how many data points? 1, 2, 3, 4, 5 data points, right? And you might say, well, I want to model those data points with a linear equation, right? So what do I do? Well, I don't know. Have you guys ever done this on the calculator? You can plug these into your TI-83 if you have one. And if you go to regression, you can click on it, and it'll actually plot and come up with the equation of a line. The thing is, it doesn't tell you how it does it. Okay, but here is the line y equals 1.8566x minus whatever. What do you think? Is that a pretty good model for the data? Steve likes it. Anyone not like it? Look all right? I mean, it almost hits data point number 4, right? Which one looks like the worst fit here? Well, number 1 or number 2? Well, yeah, that's the thing, right? Wouldn't you rather use a quadratic model here? Doesn't it look like they kind of line a parabola? I mean, let's look at that for a minute. Or a cubic. Here's a parabola. So someone did a quadratic regression. That looks a little nicer. You know? And you can do exponential regression with an exponential function. You can do all kinds of various regression equations. And they all are based upon, well, the idea that we're going to show you here in the book. Okay, so when you are trying to measure how good the model does, how well the model does, okay, what you do is you add the squares of the differences between the actual y values and the values given by the model. So I should show you on the picture what we're talking about, but here, let's go to the picture and then we'll come back to the equation. See, here's a line that doesn't hit any of those 3 data points, right? But what we have is we have error. There's positive error here. I guess we call that negative error there, and positive error there, right? And when you subtract, you know, what is this? This is x3 comma f of x3. If this is the line y equals f of x, right? So you're subtracting, I guess, the difference in the y coordinates because the x coordinates are the same. See that? Of course, then if you subtract them up here, so here's x2 comma f of x2. If you subtract them up here, then you'd have the sign the wrong way, right? And you don't want the positives and negatives to cancel each other out, so what we do is we square the errors before we add them. Okay? And we add up those squares, and we call that number. Well, who cares what we call it? They call it S. Your book calls it S. The sum of the squared errors. By the way, a lot of times you will see this. These squared errors are sometimes called residuals. That's a word you'll see again at some point. Residuals. Okay? So, you know, we're trying to figure out, well, what are we trying to do here? The goal, the goal here is to minimize S. Where again, S, if you look at what it was, there it is, right? The sum of the squared errors from I equals 1 to n if you have n data points. All right, so how do we minimize S? Well, it'd be nice if we could write S as a function, right? So actually, in this example, what is S a function of? Well, basically, if I give you a line, you can compute S, right? Like, let me do a different line. Is that line better or worse? Why is it worse? Well, that's about the same, but these are much worse, right? I have more, bigger residuals there. You guys with me on that? Okay. So you can try all different kinds of lines. How are you going to get the best one? Yeah. Well, how do I compute it? See, S depends upon the line, right? Now, how do you specify a line? What do I have to give you if you want to? You both answered at the same time. I'm sorry. Go ahead, Steve. You need points. How many points? 2. So if I give you 2 points, you know what the line is. Okay. What were you going to say, Adam? X and Y. What do you mean? Uh-huh. Just like he said, if I have 2 points. Of course, if I have 2 points, and suppose I want to write the equation of the line, what do I do? I compute the slope, and then I need to use one of the points, right? And actually, yeah, a lot of times we use the y-intercept. So if you want to, you could say that S here is actually a function of, how about I use these letters? M and B, right? Because if I give you a slope, and if I give you the y-intercept, then really I gave you the line, and you ought to be able to compute S. You guys with me on that? All right, so let's show you how this works. Let's see. If I want to, okay, so let me, so suppose f here is going to be, f of x is the function mx plus b, right? Then s of m comma b will be, well, it's a sum, I equals 1 to n, oops, I equals 1 to n of a bunch of things squared. Now, what is it that's squared? Well, like I said, you're subtracting the function value on the line from the data point value. So what I'm subtracting would be mxi plus b, right? That's the function value, where I is one of the data points. And what am I going to subtract from it? yi. Okay? Now, I realize that's an ugly equation, but you have to understand something. The only variables in that equation are m and b. Right? Because I have all the data points. You guys follow that? Okay. So now what do I do? Well, let's take the partial derivatives. So let's see. What partial derivatives do I want? Yeah, so let's call it Sm, okay, of Mb. Now what's that going to equal? Well, that's going to equal the sum I equals 1 to n, because you could do it term by term. And let's use the chain rule. 2, and then, okay, what's the derivative? So it'd be mxi plus b minus yi to the first power. And then the chain rule says, well, I have to multiply by xi, right, because those are constants. The m was the variable, that's right. So we could put in xi in here. And then you have it. How about SB of MB? Well, that's I equals 1 to n. And let's see, I get a 2 again. And I get mxi plus b minus yi. That's just times 1, right? Because the derivative of b is 1. So there it is, partial derivatives.
Wait, bro. X sub m.
Yep.
That's x1. Between 2 and
That's xi.
oh.
So actually, you have to do it for each particular term that you have. For each data point, you have to pull that out, that number. You guys okay? So then what do you do? Well, we want the critical points, right? So we're going to set these things equal to 0, right? So basically, I want to solve this system of equations. What's that? Can we cancel sums? What do you, uh-huh. guess the one weird thing is you have that extra xi up there, right? He's the killer. This guy right here is the killer, that xi. So let me show you what you can do, okay? So I'm going to do a little move. I'm going to, first of all, divide by 2, right? Get rid of all those 2's. And then I'm going to move the yi terms to the other side. All the yi terms are going to go to the other side of the equation. And when I do that, here's what I get. I get m, which I factored out, times the sum, and I'm not going to write I equals 1 to n anymore because it's getting annoying, times the sum of the xi squareds, right? Because I had xi times another xi. Okay? Plus b times the sum of the xi's, because again, that xi got distributed. Okay? And then equals, can you tell me what it's going to equal? Almost. Sum of the xi, yi. Because I had to distribute that little xi that I got from the chamber. Okay? How about the second equation? Well, I guess I get, let's see, the sum of the, well, I get m again. M times the sum of the xi's this time. There's no xi squared for this one. Plus, oh no, this is a little tricky. B times what? Well, 1, except that you're summing it from 1 to n. So what's this? I equals 1 to n of 1. 1 plus 1 plus 1 plus 1 n times is n. Does that make sense? Because there's n data points. Each one of them has a 1. So really I'm going to have b times n. And that's going to equal what? Well, the sum of the yi's. Okay? So this is a quick way of writing down all those equations that you're really getting. Oh, it's 2 equations, but it just has lots of pieces because of all the data points. So now, this is where linear algebra helps out a little bit in terms of presenting it, and your book does not do this. But what you can do is you can write a little matrix equation from this. So people with linear algebra background are going to recognize that, oh, wait a minute. Let's put the m here and let's put the b here, because really this is a linear combination of m and b. Or it's a matrix multiplication by m and b. If you know how to multiply matrices, what I write down here probably will make sense to you. I'm going to put sum of the xi squared here. I'm going to put sum of the xi here. I'm going to put sum of the xi here. And I'll just put what here? N. And this equals, well, this crazy matrix. Sum of the xi, yi. And sum of the yi's. So there it is. If you could solve that equation, that linear system, solve for m and b, then you have the answer. You have the least squares line. And this is what your computer does. It knows how to solve that system. And so it gets m and b by itself and tells you what it is based on these quantities. That's for linear. Well, actually, for quadratic, it is no harder. It just takes a little longer. Well, not for a computer. But for a quadratic, the only difference is, you're trying to fit something that looks like this. F of x equals, let's call it ax squared plus bx plus c. So you're trying to fit 3 variables instead of 2. into the data. Okay? So for a quadratic fit, you get a 3 by 3 matrix. And it's very beautiful. It's sum of the xi cubes, sum of the xi squareds, sum of the xi's. It's the same beautiful symmetric matrix, and again, there's an n at the bottom. And it works exactly the same way. And that's why I always want to show people the linear algebra, because then all of a sudden you realize, wow, it doesn't matter what kind of polynomial I fit. It's just as easy as the linear one. Now, if you ask how do they do an exponential, I'm starting to push myself a little bit. I'm not quite sure. I think that an exponential fit happens from the fact that we know that E can be written as a power series, so you can do some of this. But I'm not sure, because the exponential of a matrix is a little tricky. So those are good questions for the programmers. Here's what your book tells you about this. It wasn't enough for my tastes. They tell you, hey guys, if you want a least squares regression line, here's what it equals. By the way, this A is what we called M. Right, that's the slope. So that's the slope, and there's the y-intercept. And you could use these formulas and solve the problems in the book. I don't think I assigned any. But I just wanted to at least talk about it for a little bit. Notice the stuff that's in the solution. Those are the pieces of the matrix, right? Nothing real fancy here. I think you'll find that denominator probably is the determinant of the coefficient matrix, because that's usually involved in the solution. Any questions on this? No? We had enough. All right, let's go back to the problem you guys just worked on. We want to build a rectangular box with an open top. Volume V. What should be the dimensions of the box to minimize surface area? So, yeah, my suggestion was, let's do this. Let's write S equals xy plus 2xz plus 2yz. Right. Right, because you're trying to minimize surface area, right? So V is a constant, right? So since V is a constant, I guess I'll solve for Z, and Z is whatever my favorite number is over xy. So now I come back to here, and I'm going to write surface area as only a function of x and y, right? This is how I reduce the number of variables. So I get, let's see, xy plus 2x times, well, v over xy plus 2y times, remember v is a constant, not a variable, v over xy. Okay, so let's see. That's xy plus 2v over y plus 2v over x. So there's my function s. Okay, so what do? Well, we compute sx of xy, right? So I get y plus, well, 0, right? Because we treat the y as a constant. And then this is 2vx to the negative 1. So I'm going to get minus 2v over x squared. Does that look right? Okay. And then similarly, because you have symmetry, sy of xy will be, well, if you work it out, you get x minus 2v over y squared. Okay. So we want to set these guys equal to 0. So let's see. Set these each equal to 0. I have a little system of equations to solve. And then, I don't know. I mean, I guess the question is, how do I solve it? And this is where, you guys notice on the homework, the algebra can get tricky. I think what I would do is I would take that first equation and I would say, well, y equals 2v over x squared. And And now I'll substitute into the second equation. So I have x equals 2v over, and I would put that 2v over x squared in for y. So I get, let's see, x equals 2v times x to the fourth over 4v squared. Basically, instead of dividing by that fraction, I'm going to multiply by the reciprocal. And so that's going to be, let's see, x to the fourth over 2v. So, you know, from this equation, you ought to be able to solve for x. Let me do that. I have x to the fourth equals 2vx. So x to the fourth minus 2vx is 0. So x times x cubed minus 2v equals 0. So one critical point I'm going to get when x is 0. The other one I'm going to get when x is the cube root of 2v. Okay? So it seems like the cube root of 2v is what I want. And if I do then y using this equation that I have in the rectangle here, I think you get y as the cube root of 2v also. And you should, so that's good. And then how am I going to get z? Well, z is going to be v divided by, well, the cube root of 2v times the cube root of 2v. And if I work that out, let's see. I get the cube root of v in the numerator when I reduce over, well, the cube root of 4, but you can multiply by cube root of 2 over 2. So let's see, it looks like I get, if you simplify, the cube root of 2v over 2. Okay, so here's your dimensions. X, y, and make z half as big. Make z half as big. You guys follow it? Cool. Yeah, so if you want to do this problem and make it a nice problem for somebody, give them a nice value of v. Give them something like 4, so that when they multiply by 2, they get a nice cube root, and they can do the problem. Okay? Why is z half as big? I simplified this mess here. I could work it out. Let's see. Z equals, right now I have v over, I have 2v to the 2/3 power, right? So that's v over, well, let's just write v to the 2/3, okay, times 1 over 2 to the 2/3. And so this is going to be v to the 1/3. And I guess I claim that this is actually going to be 2 to the 1/3 over 2. Because if you multiply by 2 to the 1/3 over 2 to the 1/3, that's how you'll get the 2 to the 1/3 over 2. And so that's exactly what I wrote for the z. Okay? Cool. Well, we're on break time. After break, we're going to come back and revisit this problem again using the method of Lagrange multipliers. We'll see if you like it any better. The theme is going to be add an extra dimension once again. I'd love to